Today's lesson, titled Measuring Correlation Strength and Constructing a Linear Regression, is probably one of the most important lessons you'll see in statistics because we're learning two critical pieces of information. First, how you measure correlation strength, and next, how you can construct a linear regression to predict future values. So you have two objectives. The first is you'll be able to calculate the Pearson's product moment correlation coefficient and interpret its meaning. And then the second is you'll be able to develop a least squares regression line and interpret its meaning as well. So let's get started. The first concept we need to cover is the Pearson product moment correlation coefficient, also referred to as R when you're working with statistics. And it's a numerical value used to measure the strength of a correlation, whether two variables are strongly or weakly correlated and in what direction. So the Pearson's correlation coefficient, also known as R, can be between -1 and +1. It has to take on values in between -1 and +1. And you'll rarely actually see -1 and +1 because -1 means you have a perfect negative correlation. That's what the negative means. And +1 means you have a perfect positive correlation. The two things move together perfectly. And if you have an R value of 0, there's no correlation at all. This table on the right is a useful tool because it gives you an idea of when you have a weak, moderate, or strong correlation. From 0 to 0.25, you have a really weak correlation. From 0.25 to 0.5, you have a weak correlation. Once you get above 0.5, now you're looking at moderate correlations, and anything above 0.75 can be viewed as a strong correlation between two variables. From here, I'm going to show you guys how to work with Google Sheets and create a data set that's ready to calculate R and then a linear regression. So I'm now going to show you how to work with Google Sheets to collect and calculate all the necessary information before making our major calculations of R and then linear regression. Now what I'm going to do is show you how to calculate R in a linear regression for the following data set. I collected 10 student heights and their associated shoe sizes, and I want to see if there's a relationship between the two and then create a line that can predict that relationship moving forward. As you can see, I've already formatted this so that I've calculated the mean using the average function, and I've also calculated the sum using the sum function of this data right here, as well as my y values of my dependent variable, which is the shoe size. What I'm going to need to do is now calculate x minus x bar, which is the x value minus the mean for each data point. Same thing with the y values. Then I'm going to square those values for both x's and y's, and then I'm going to multiply those values, x minus x bar times y minus y bar. All this data will then be used to calculate R and our correlation coefficient. So follow along closely. The first thing I'm going to do is x minus x bar. So all I'm going to do is I'm going to type in my equal sign, telling my Google Sheets that I want to create a formula. And I'm going to do my x value, 63, minus my mean value of x, which is 63.45. And I'm going to hit enter. And all that does is it does 63 minus 63.45. It gets me -0.45. Now, because I want to repeat this process for all those values, there's a shortcut I can use. The first thing I want to do is I'm going to lock this cell, this mean value cell. And so I'm going to click on this formula I created where it's C4 minus C14, C14 being the mean. And I'm going to put a $ in front of the C in the C14 and a $ in front of the 14. What that does is it locks the mean value. This is useful because once I lock it, now I can drag this box down and it's going to repeat this formula for all these cells right here. And as you'll see when I click on any of these cells, that C14 is locked with those $, but it is changing which x value I'm subtracting from. So this is going to be C5, C6, C7, and those correlate to these x values. I'm going to repeat this process for y. So I'm going to do equals my y value minus my y mean, which is 6.85. I'm going to hit enter. I'm going to go into this function. I'm going to insert these $ here to lock my mean cell. Hit enter again, should be the same value, but then I'm going to drag it down. So now I have all those y minus y bars. The next thing I'm going to do is now square the values I calculated in column E. So I'm going to hit equals, hit the value right there. I'm going to use the caret symbol to say I'm raising it to a power. I'm going to raise it to the second power and hit enter. I got 0.2. Then I'm going to drag this down because I want to repeat this formula, and it repeats the formula for all these other x minus x bars. I'm going to do this again now. This time I'm going to do it with the y values. I'm going to square it and then drag down. Then the last thing I'm going to do in this last column is I'm going to multiply my x minus x bar, and I'm going to use this little star symbol here, times my y minus y bar, and I'm going to hit enter. That multiplies these two values here, and then I'm going to repeat this process down by dragging, so I have all those values. And I also want the means and the sums of all these columns just in case I want to use those. So I'm going to click on this box right here and drag across. That's going to take the mean of all those columns. And then I'm going to drag across here, and that's going to take the sum of all the columns. And now I have all the data I need to actually calculate R and then a linear regression line. So what I have here is a screenshot of the data table that I just created in Google Sheets. And what I'm now going to do is show you how you can calculate the deviations, which we'll then use for a linear regression and the correlation coefficient. So there's three standard deviations that we need to calculate. The first is the standard deviation of our x values, which in this case is the heights, then the standard deviation of our y values, which is the shoe sizes, and then something called the covariance, which is marked as S subscript xy. The formulas for these, it's the sum of x minus x bar squared divided by n. Same thing for y, just with the y values. And then the covariance is the sum of x minus x bar times y minus y bar divided by n. Now, all we really need to do is gather the necessary information to substitute into the formulas and solve. The good thing is that's going to be easy now that we've created this table. So we're going to use these three values here. That's the sum of x minus x bar squared, the sum of y minus y bar squared, and the sum of x minus x bar times y minus y bar. The n's for all these formulas are going to be 10 because we have 10 observed observations. So now I'm going to do my substitution. I substituted these three values into their appropriate locations, divide them all by 10. So from here, all I need to do is substitute that into my calculator, and I get my three standard deviations. Standard deviation of x is 1.27, standard deviation of y is 1.57, and the covariance is 0.418. Now that we've done that, we're actually ready to calculate our first key statistic. We're going to calculate Pearson's correlation coefficient, which is R. Notice I have my standard deviations located right here because those are the values that I'm going to use when calculating R. Because the formula for R is the covariance divided by standard deviation of x times the standard deviation of y. A fairly simple calculation. We've done most of the hard work already. So I'm just going to substitute. Our covariance is 0.418, that's my numerator. My standard deviation of x is 1.27, and my standard deviation of y is 1.57. I substitute this into my calculator, and what I get is R is equal to 0.210. And if we refer back to our table of R values, this is close to 0. So we would call this a very weak positive correlation between height and shoe size. It's very weak because our R value is low, and it's positive because our R value is positive. So contrary to what you may think, based off the data we have here, there's a very weak connection between how tall you are and your shoe size. Now, this could be due to a lot of different issues. It could be due to the fact that I only had 10 data points instead of what would normally be about 100, 200 plus. And the other reason is maybe there actually isn't a very strong connection between these two variables. So we're now going to transition into calculating our least squares regression line, also known as an equation in y equals mx plus b. And the regression line for y on x is a more accurate version of the line of best fit or trend line. So oftentimes you'll see a scatter plot with a trend line. The trend line is kind of like a general sketch, but the least squares regression line is really a formal way of creating a linear model to map our data. And the purpose of it is the least squares regression line is used to predict values of y for values of x. This is huge. The whole purpose of developing a least squares regression line is it's a predictor. I have here just a basic example. This is heart rates before and after a brisk walk. So it's a way you can predict here whether your heart rate before a walk can determine your heart rate after a walk. And what they did was they plotted all the data, then created a least squares regression line through that data. So what I'm now going to teach you is how you can actually create your least squares regression line by hand. So we're going to continue with this data set and the standard deviations that we created before. Now we already know that there's a weak correlation here because our R was 0.2. However, we're still going to work through a linear regression line so you can see how it's done. Now the first formula you need to use is the following formula. Y minus y bar equals SXY, which is our covariance, divided by our standard deviation of x squared times x minus x bar. Now, this is technically in what you'd call a point-slope form. We're going to substitute and then transition to our slope-intercept form, y equals mx plus b. Now we have our y bar, that's our mean. We have our x bar, that's our mean for x. We have the covariance, which is 0.418, and we have our standard deviation of x, which is 1.27. So the first step is just basic substitution. I substituted all those values in. The next thing I'm going to do is I'm going to simplify this fraction. I'm going to square 1.27 and then I'm going to do 0.418 divided by that value. When I do that, I get the following answer. Y minus 6.85 equals 0.259 times x minus 63.45. The next thing I'm going to do is I want to now transition this into y equals mx plus b, the more common slope-intercept form of a linear equation. So to do this, I'm first going to distribute. I'm going to distribute my 0.259 to the x and to the 63.45. When I do that, I get y minus 6.85 equals 0.259x minus 16.43. The last step is getting y by itself, and to do that I'm just going to add 6.85 to both sides. When I do that, I get y equals 0.259x minus 9.58. This right here is your regression line. We did it. We've calculated, and this regression line tells us that it has a gradient, which is another way of saying a slope of 0.259 and a y-intercept of negative 9.58. This was a dense lecture, but you now have the skills to both calculate your Pearson's correlation coefficient and develop a linear regression. Good luck on the assignment.